All right, so this is going to be the second of the three different versions of the key takeaway of this lecture, that in general, deviating from the longest chain consensus protocol can boost the rewards of a node. So last video, we saw that in sort of this extreme case where you had a really big node with more than half of the hash rate, where obviously a lot of other things go wrong as well. And we're going to see in this video that actually, under our current assumption of worst-case tie-breaking by honest nodes among competing longest chains, under that assumption, actually, it does not matter how big you are. No matter how small you are as a node, it will, in general, be profitable to deviate from longest chain consensus. Then in the next video, we'll do the third and most difficult argument, which is where we show that a version of that key takeaway is true even in the case that honest nodes tie-break in the best possible way for themselves. So the deviations from honest behavior that we're going to be talking about sometimes go by the name selfish mining. Selfish here just meaning that the nodes are doing profit maximization rather than just obediently following a protocol. Mining is just referring to the usual name for block production in a proof-of-work blockchain. And indeed, this work we're going to talk about on selfish mining, this video and next video, it actually dates back pretty far. It dates back to 2013, I believe is when it was first kind of disseminated, formally published, I believe, in 2014. This is by Eyal and Sarir. So at the time that they did that work, right, 2013 or so, Bitcoin was, for the most part, almost the only game in town. So naturally, they were going to focus on Bitcoin, in particular Nakamoto consensus. And as we'll see, the attacks we're talking about, selfish mining, is pretty specific to Nakamoto consensus. These days, people also sometimes use the word selfish mining in a much broader sense, which is just kind of any deviation from intended behavior by block producers that's motivated by increasing their revenue. So for example, deviations that sort of increase the amount of transaction fees that a block producer might collect, or the amount of revenue they get from the application layer, which sometimes goes by the name MEV. So sometimes selfish mining has sort of this broader connotation of just any profit-motivated deviations from honest behavior. But in this lecture, we're going to focus on sort of the original narrow meaning of the phrase selfish mining, which is the specific deviations identified by Eyal and Sarir, specifically for boosting the share of block rewards that a node earns in Nakamoto consensus. This is actually a fairly famous result, at least in the academic sphere. Last time I checked, this paper by Eyal and Sarir actually had a higher citation count than any other kind of formally published paper concerning blockchains. Like the Bitcoin white paper, has a higher citation count. But if you're talking about sort of formally published research papers, last I checked, this one was #1 on the leaderboard. Also, on a personal note, when I saw this work, at the time, it definitely made a big impression on me as well. I mean, I was aware at that time of the Bitcoin protocol. Certainly thought the Bitcoin protocol was cool. I don't know that I'd really started thinking about it as like a bona fide research area in its own right. And then when this paper by Eyal and Sarir came along, I realized that sort of, especially on the game theory side, maybe there's a lot more depth here than I had originally realized. All right, so let's get into it. So like in the last video, we're going to be thinking about the case where some portion of the hash rate is honest and just doesn't think about profit maximization and just obediently follows the protocol. And then a single node is going to be contemplating whether or not it should also be honest along with everybody else, or if there's some deviation that would boost its share of the block rewards. Now, unlike in the last video, this node that we're contemplating, node A, that's going to have some hash rate alpha, which is less than 1/2. So again, in game theory language, we're going to be proving that obediently following longest chain consensus does not constitute a Nash equilibrium. There will, in general, be an incentive for nodes to unilaterally deviate from that outcome. So as in the previous video, if node A just kind of, conforms and also, like the other nodes, follows the protocol honestly, right, then the chain is just going to grow in a very orderly fashion. Node A will have proportional representation of the blocks produced and therefore of the blocks on the longest chain. So it will get an alpha fraction of the block rewards if it is honest. So the question is there any other strategy that would boost its share of the pie to a fraction bigger than alpha? To see that the answer is yes, let's talk about a strategy, which is, very much motivated by the same strategy we used in the 51% case in the last video, let's think about a strategy where node A, it's trying to sort of accomplish two different things. So first of all, for the blocks that it produces, it obviously wants as many of those to get onto the longest chain as possible, right? You only get block rewards if you're on the longest chain. So node A, ideally, it gets all of its blocks on the longest chain. That was certainly true in the last video in the 51% case. And then secondly, right, so in addition to sort of having as many blocks as possible on the longest chain, it also wants there to be as few other blocks as possible on the longest chain. That's how it maximizes its share of blocks on the longest chain, so which is its share of the pie. And so that means, right, it needs to fork, it needs to orphan as many honestly produced blocks as possible. Now, last video in the 51% case, we had a strategy that actually was able to orphan all of the honestly produced blocks. None of them got onto the longest chain. With a smaller node, that's no longer going to be possible, but still you'd like to approximate that to the extent that you can. So as much as possible, you'd like to orphan as many honest blocks as possible off of the longest chain while making sure all of yours get in. So that's the plan. Before I sort of write down formally what this strategy is, let's actually just talk through how it's going to work in an example. I think once you sort of see the example, it'll be kind of pretty clear what the more general strategy is. So let's assume we're just kicking things off with a genesis block, B naught. So now we're doing Nakamoto consensus. All the nodes running the protocol just keep trying to solve the hard crypto puzzles, and by the random oracle assumption, your probability of being the next leader, of producing the next block, is proportional to your hash rate. So in other words, there's an alpha chance that the next block is going to be produced by node A. There's a 1 minus alpha chance it's produced by someone else, which would be an honest node. So let's, for the example, assume that the next block is produced by an honest node, which again is a better than 50% chance, a 1 minus alpha chance. All right, so that's the block B1. Okay, so that's an honestly produced block, and we would like to orphan it from the longest chain if possible. How would we orphan it? Well, node A would try to produce its own alternative block, also extending the genesis block. So once B1 is announced, all of the honest nodes, obviously, they're just going to be trying to extend the longest chain. They're going to be trying to extend B1. This node A is going to try to extend the genesis block. And again, there's an alpha chance that node A does in fact extend the genesis block before any of the honest nodes extends B1. So if node A in fact succeeds and produces an alternative block B1 prime extending the genesis block B naught, then, again, this is because we're using adversarially chosen tie breaking by honest nodes. As soon as you have a tie between an H block B1 and an A block B1 prime at the same heights, the adversary can just arrange that anybody, right, so node A or an honest node is going to wind up extending the A block B1 prime. So if node A successfully produces B1 prime, then B1 is orphaned. But remember, node A only has alpha fraction of the hash rate, so that definitely may not happen. And for the example, let's actually assume that the next block is also produced by an honest node. So that's going to be a block B2 extending B1. Now, if this happened in the last video when node A had 51% of the hash rates, remember there, basically node A was unwilling to tolerate even a single honestly produced block on the longest chain. So in the last video, node A would just keep on, even though now B2 was created, it would still keep trying to extend the genesis block B naught to orphan all of the honest blocks, including B1. And it could get away with that because it had 51% of the hash rate and it was producing blocks faster than all of the honest nodes combined. Now that is not true in this video, right? So node A, it's actually producing blocks less frequently than the collective of honest nodes, which means that sort of once it's behind, right, in the way now it's behind by sort of 2 steps on the sort of honestly produced chain, there's a real chance that it will never actually catch up. And so that would be a bad strategy to just keep trying to extend B naught. So instead, here, node A is going to be like, all right, fine, I'll concede the honestly produced block B1. Let's allow that to be in the longest chain. But let me at least try to orphan off this more recent honestly produced block B2. And so what that means is that the node A is going to switch from trying to extend B naught to trying to extend B1, trying to produce an alternative block B2 prime, extending B1, thereby orphaning B2 if it succeeds. And let's now assume actually here that node A does succeed. So let's assume that the next block produced is produced by node A, so that's going to be a B2 prime extending B1. And as we discussed, because we're assuming adversarial tie breaking by honest nodes, once B2 prime shows up, it's as if B2 doesn't exist, right? So node A, of course, it will extend B2 prime itself just by choice. And then any honest node, the adversary can just say, oh, well, break ties among these two equally longest chains in favor of B2 prime. So B2 never has a shot at ever being extended again. Obviously, it's not going to wind up on the longest chain. It gets orphaned. All right, so now from this example, you should have pretty strong intuition about one of the ingredients into this strategy, this deviation from honest behavior. But there's also a second really important ingredient, which actually we did not have in the last video. We did not need when node A was 51%. And the rest of the strategy is really going to take advantage of the ability of a node to delay block announcements. And we talked about this back in the context of like consistency and liveness in lecture 8. We said, okay, well, back then we were thinking about Byzantine nodes. We're like, what could Byzantine nodes do different than the longest chain consensus? They could choose a predecessor that's not the end of the longest chain. They could sort of, produce empty blocks or just sort of censor transactions. And they could, if they wanted, not announce their block immediately. And in lecture 8, the only purpose that served was kind of to make our proofs more annoying, right? In our consistency and liveness proofs, we wanted to handle Byzantine nodes that delayed block announcements because that's something they could obviously do. So we certainly wanted our proofs to handle it. But it didn't actually affect sort of where the threshold was. We still got consistency and liveness as long as you had more than 50% honest hash rate. Here we're going to see that the ability to delay block announcements is really going to matter. And it's actually really directly useful for nodes that want to boost their share of the block rewards. So to see how this works in the example, right? So at the moment, all of the nodes are trying to extend B2 prime, right? Node A just sort of by construction of its strategy, all of the honest nodes by sort of adversarial tie breaking. Everybody's trying to extend B2 prime. Someone's going to succeed. Let's assume it's node A that succeeds in creating a block B3 prime. So node A, if it wanted, could go ahead and announce this block B3 prime as soon as it's created. But there's actually something more strategically clever it can do. Okay, so in this strategy, actually what node A is going to do is going to keep quiet, keep private the fact that it created this block B3 prime. That's why the block is kind of in a dotted line and the predecessor arrow is in a dotted line. That means that node A is actually keeping to itself that it created this block B3 prime. All right, so why is this helpful to node A? How is it beneficial to keep private the existence of block B3 prime? Well, let's think about sort of the world where it's private and the world where it's public. Okay, so imagine that node A did just sort of broadcast B3 prime immediately to everybody. Then what would happen? Everybody would know about this sort of full magenta in-tree, and everybody would be trying to extend block B3 prime, right? That's the end of the longest chain, so that's what the honest nodes are going to be trying to extend. Node A, of course, will also be trying to extend its own block. And that means that if an honest node succeeds, right, in extending the publicly announced block B3 prime, that's going to be a block B4, okay, which goes at which is going to be the new end of the longest chain. So that B4 would be an honestly produced block that has a legitimate shot at winding up in the longest chain at the end of the day. And remember, the point of this strategy is to keep honestly produced blocks off of the longest chain as much as possible. So suppose instead node A actually did keep B3 prime private. How would that change things? Well, node A would be doing exactly the same thing either way. Node A knows about block B3 prime either way. It's going to be trying to extend its own block either way. But if B3 prime is private, if honest nodes do not know about it, then they're only aware of the blocks up to B2 and B2 prime. And again, by adversarial tie breaking, they're all going to be trying to extend B2 prime. And so that is wasted work, right? You have tricked the honest nodes at this point into trying to extend a chain which is not the longest, which means any successes they might have, you are in a position to just completely waste, to completely sort of cancel out. So to see exactly how this works, to see exactly how node A is basically going to nullify any honestly produced blocks in this case, let's actually assume that the next block created is also by node A. So that's going to be a block B4 prime extending B3 prime, which again, that node A will keep private from all of the other nodes. So once this happens, node A will keep trying to extend its own latest block. So it'll try to privately extend to B4 prime. The honest nodes at this point do not know about B3 prime or B4 prime, so they're going to extend to the end of the longest chain that they know about, breaking ties adversarially. They're going to be trying to extend B2 prime. And now suppose that is actually the next thing that happens. Suppose some honest node does successfully create a block, which is going to name as a predecessor block B2 prime. So now is the moment in time where node A can say, haha, I tricked you. You were trying to extend something other than the longest chain. Yes, you produced a block, but I can make sure that it gets orphaned. So as soon as some honest node announces B3, node A is just going to announce its competing block at the same height. So it's block B3 prime. And then again, you're going to have a tie for the longest chain by adversarial tie-breaking. Honest nodes, given the knowledge of both B3 and B3 prime, are going to work to extend B3 prime. B3 will never get extended. It will never wind up in the longest chain. So B3 gets orphaned by the announcement of B3 prime. So let me now actually sort of write down the strategy. But again, the strategy, I think you're going to know exactly what this is just from talking through this example. Again, there's sort of two main ideas. So one idea is that, like in the 51% case, we're going to try to orphan honestly produced blocks off of the longest chain. But we're not going to be as stubborn as we were in the last video because we don't have the sort of advantage of having 51% of the hash rate. And so node A is only going to try to, if the longest chain concludes with multiple honestly produced blocks, node A is only going to try to orphan the most recent of them. So that's idea number one. And then idea number two is a sort of delayed block announcements. So if node A is actually creating blocks that get it ahead of the honestly produced blocks, it's going to release the announcement of those blocks only on a need-to-know basis in order to make sure that all honestly produced blocks during that period wind up getting wasted. So the strategy is going to have two cases, depending on, in effect, who's ahead, whether node A is ahead or whether the honest nodes are ahead. So what do I mean by that? Well, let's let h, little h, denote the biggest height of any block that's been produced thus far. And again, remember, by block height, we just mean the number of steps since Genesis. So like in our example at the bottom of the slide, B0 has height 0, B1 has height 1, B2 and B2 prime have height 2, and so on. So among all the blocks that have been created, and again, these may or may not have been announced, right? There's blocks that everybody knows about, there's blocks that only node A knows about, but among all of the blocks that have been produced, little h is the highest block height of any of them. So for example, in the bottom slide, little h would be equal to 4 because of the secret block B4 prime. So in case one, we're thinking about, node A is in the advantageous position. Node A is ahead, meaning that there exists a block at height h that was produced by node A. So for example, that is the case at the end of the example that we talked through, because B4 prime was produced by node A. And of course, in this case, the strategy for node A is obvious. It should just try to extend its own block, right? It wants to just, it's already winning. It's already kind of got the tip of the longest chain, so it may as well just sort of make that even longer. This is also the part of the strategy where you delay block announcements. So in case one, if node A succeeds in producing a sort of an A block at an even higher height, it keeps that quiet for now. So in our example, we saw this part of the strategy in action, for example, when block B3 prime was created extending B2 prime, and similarly when B4 prime was created to extend B3 prime. So the second case is where the honest nodes have the advantage. So the highest block height was produced by an honest node. So for example, very early in our example, we just had the blocks B0 and B1, where B1 was honestly produced. So that would be an example of when you're in this case too. So at no point do you worry about blocks at heights lower than little h, little h minus 1, little h minus 2, etc. There may well be honestly produced blocks at those lower block heights that belong to the longest chain now and forever. And that is just sort of something node A has to accept, okay? Because it doesn't have 51% of the hash rate, because it has less than that, it has to resign itself to some honestly produced blocks getting into the longest chain. But node A will always be trying to orphan the tip of the longest chain if it was honestly produced. How does it do that? It tries to produce a competing block at the same height, little h, extending the same block that the honestly produced block does. And then if it succeeds, right, again, using adversarial tie breaking, that's going to wind up orphaning at least that most recent honestly produced block. If node A does succeed in this case too, there is absolutely no reason to delay the creation of its block. It should announce that immediately, because that has the desired effect of orphaning this other honestly produced block at height h. So to complete the description of the strategy, we just have to say, for the blocks created by node A while in case 1 of the strategy, when do those blocks in fact get announced? They don't get announced immediately, so when do they get announced? And this you already see from the example. Okay, they're announced on a need-to-know basis. So if as part of case 1, node A creates some block at some block height little h, it waits until the honest nodes create a block at that same height little h, and then and only then does node A announce its previously private height h block. Having described the strategy, let's proceed to its analysis. So remember the comparison we're interested in, right? Node A, if it wanted to, could obediently follow longest chain consensus, and we're contemplating instead this alternative strategy, this deviation. And we know what happens if it sort of obediently follows longest chain consensus, then there's going to be no forks. All blocks produced are going to wind up on the longest chain, and node A is going to have an alpha fraction of those blocks. And so the question is whether or not this strategy boosts node A's fraction of blocks on the longest chain to something bigger than alpha. So that's what we want to understand. So the analysis is going to have 3 steps, and I want us to focus on a sequence of some reasonably large number, capital N, of rounds. Okay, so capital N blocks in a row that get produced, right? Some of these are going to wind up on the longest chain, some of these may not wind up on the longest chain. So just capital N consecutive creations of blocks. And think of capital N, I don't know, think of it as in the thousands, say. All right, so the first observation is if we think about these capital N blocks, again, some may be on the longest chain, some not, but we don't worry about that. We just think about these capital N blocks. We expect an alpha fraction of those to be produced by node A and a 1 minus alpha fraction of those to be produced by the honest nodes. And this is just the exact same argument we used in the Sybil resistance or proof of work using the random oracle assumption. The probability that you're the next one to create a block is proportional to your hash rate. So that's an expectation, an alpha fraction of the blocks we're expecting from node A, 1 minus alpha fraction from the honest nodes. But if capital N is decently large, then with high probability, the actual numbers are going to be very close to these expectations. That's basically the same kinds of proportional representation arguments that we made back in lecture 8 when we were analyzing randomly chosen leaders. So there'll be a little bit of variance around these expectations, but we're just going to ignore that for the sake of this argument. Now, steps 2 and 3 of the analysis, they go back to our intuition that we had a long time ago about what this strategy is trying to do. On the one hand, get as many A blocks into the longest chain as possible, ideally all of them, and then orphan as many H blocks as possible. Ideally all of them, but perhaps if you don't have 51% of the hash rate, just do the best that you can. So step 2 is going to be the observation that on the first of those goals, we do as well as we could do. That every single block created by node A will in fact be guaranteed to wind up on the longest chain. All right, so why is that true? Well, maybe the first observation is that, by construction of this strategy, whenever node A announces one of its blocks, at that moment of announcement, the announced block is in fact the end of some longest chain. So, let's go back to our example, the magenta blockchain in the lower left. So 2 cases. So first of all, block B2 prime, that was the first block created by node A. So at that point, we were working in case 2 of the strategy. So the honest nodes had a lead. Block B2 had already been created by some honest block, and node A was just trying to orphan it with its own height 2 block B2 prime. In that part of the strategy, you announce the block immediately upon creation, and you'll see that block B2 prime, when it was created, when it was announced, it was indeed the tip of one of the longest chains. Okay, there was another longest chain ending in B2, but B2 prime at the time of creation and announcement was the end of the longest chain. Now, B3 prime and B4 prime, so those were blocks that node A created and it was getting ahead of the honest nodes. So at the time of creation, if they were announced, they actually would have been the tip of a unique longest chain. When B3 prime was created, when B4 prime was created, those would have been the unique longest chain had those blocks been announced. Now they weren't. Those announcements were delayed, but they were still, announced in time for them to be the end of some longest chain at the time of announcement. So for example, B3 prime got announced by node A at the time that B3 was announced, right? And so you'll notice that if both B3 and B3 prime exist, it is the case that B3 prime is the tip of some longest chain. So given that property, given that every block created by node A is the tip of a longest chain upon announcement, what that means is that that block will be on the longest chain forevermore. Okay? Every single subsequent block is going to extend the chain that includes that A block. Why? Well, node A, obviously it extends its own blocks. It doesn't extend anybody else, so no problem there. And then for the honest nodes, again, we're going to rely on the adversarial tie breaking. So if you have a tie on the longest chains, we can adversarially arrange for honest nodes when they create blocks to also extend that A block. So at the tip of some longest chain at the time of announcement and in the longest chain forevermore. All right, so mission accomplished as far as getting A blocks into the longest chain. They all wind up there. What about the second goal of orphaning as many honest blocks as possible? Well, they're not all in general going to be orphaned. So like in our example in the lower right, you'll notice that the block B1 was honestly produced and does in fact wind up in the longest chain. But what you can say is that a lot of H blocks do get orphaned. In fact, for every single A block, every block that node A creates, you can point to an honestly created block that gets kicked off of the longest chain. So if we look at our example, the magenta blockchain in our in the lower left, you can definitely see this. So the A block B2 prime has the effect of orphaning the honestly produced block B2. Similarly, B3 prime at the time it's announced has the effect of orphaning the honestly produced block B3. At some later point in that example, honest nodes will eventually create another block B4. That's going to be extending some longest chain that they know about, and by adversarial tie breaking, that B4 will be extending B3 prime. And so then the subsequent announcement of B4 prime will knock out that honestly produced block B4 from the longest chain. And in general, right, the only time an A block ever gets announced is because there's an H block at exactly the same block height, right? And two blocks at a given height, only one of those can get in the longest chain. And because we're assuming adversarial tie breaking, it's always going to be the A block that gets in the longest chain. It's never going to be the H block. So each announcement of an A block will orphan one H block. So those are the three main conceptual steps of the argument. Now let's just do some simple calculations to figure out, as a function of alpha, exactly what fraction of the pi you get with this strategy. So let's just think about the blocks that get on the longest chain. Let's just look at how many of those were honestly produced, how many of those were produced by node A, and then look at the proportions thereof. Well, A blocks, it's quite simple. We know the total that was created. That's going to be ballpark alpha times n. And by step 2 of the argument, every single one of those gets on the longest chain. So roughly alpha n A blocks on the longest chain. So what about the H blocks? Well, we certainly have a handle on how many are going to get created overall during this period. It's going to be a 1 minus alpha fraction, roughly, of the capital N blocks. But the question is, how many of those wind up in the longest chain and how many get orphaned? And by step 3 of this argument, we see that the number that get orphaned is going to be the same as the number of A blocks, okay, which again is roughly alpha N. So 1 minus alpha quantity N H blocks get created, but alpha n of those wind up not on the longest chain, leaving you with quantity 1 minus 2 alpha times n H blocks on the longest chain. So now we can just look at the fraction of the blocks on the longest chain that were created by node A and compare that fraction to alpha. So the numerator is going to be the number of A blocks on the longest chain, which is going to be roughly alpha n. The denominator is going to be the total number of blocks on the longest chain, which is the same thing as the total number of blocks which are not orphaned. And since an alpha n number of blocks are orphaned, that leaves 1 minus alpha quantity times n on the longest chain. Then, of course, the n's cancel and leave us with the ratio of alpha over 1 minus alpha. So that wraps up the analysis, culminating in this fraction alpha over 1 minus alpha. How should you interpret this? The key point is that for any alpha positive, no matter how small, for any positive alpha, 1 minus alpha is going to be less than 1. And so alpha over 1 minus alpha is going to be bigger than alpha. In other words, no matter how small you are, no matter how little hash rate you have, you will get a boost in the size of your slice of the pie by using this strategy rather than obediently following longest chain consensus. So for example, you could imagine a node that has, say, a third of the overall hash rate, so alpha equals 1/3. Rather than merely getting 1/3 of the block rewards, as you would by obediently following the protocol, with this deviation, you're going to get 50% of the block rewards, as usual, assuming that all of the other nodes behave honestly and that ties are broken always in your favor. Similarly, if you have a 20% hash rate node, so alpha equals 1/5, you again get a boost. It's not as big a boost, but you still get a boost from 20% of the block rewards under sort of obediently following longest chain versus 25% of the block rewards, which is what you would get following this deviation. Now, the fact that selfish mining helps no matter how small you are, I got to be honest with you, that is to some extent an artifact of the tie-breaking assumption that we're making right here, that node A basically, as it deviates, can also kind of dictate how the other nodes break ties. In the next video, when we look at sort of the more difficult but also more satisfying scenario where actually node A can't make any assumptions about how the honest nodes break ties, there we'll see that selfish mining does help if you're sufficiently big. Okay, so if you have 1% hash rate, then actually selfish mining doesn't help you. But if you're big enough, turns out bigger than a third, then in fact, despite the fact that the honest nodes are sort of tie-breaking in a way to mess you up as much as possible, it's still helpful to do this kind of deviation away from just straightforward longest chain behavior. There's also a neat connection I want to point out to you between this analysis we just did and our analysis of the chain quality of longest chain consensus back in lecture number 8. So I don't know if you remember, but in lecture number 8, we were talking about the consistency and liveness properties of longest chain consensus, originally in the permission setting, but those extend to Nakamoto consensus as well. And we were saying, could you have a stronger version of liveness? And the stronger version of liveness that we looked at was proving lower bounds on the chain quality. What's chain quality? Chain quality is the fraction of the blocks on a longest chain that were produced by honest nodes. And for liveness, you definitely want a chain quality of bigger than 0, because if all the blocks are being included by Byzantine nodes, for all you know, all those blocks are empty. So the only way transactions are guaranteed to actually enter the blockchain is if honestly created blocks wind up getting included in the longest chain. So you certainly want a chain quality bigger than 0. And then the question is, as a function of sort of alpha, the fraction of Byzantine nodes or Byzantine hash rate, as a function of alpha, how high is the chain quality going to be? And we proved in lecture number 8 a kind of neat strengthening of liveness, which is that we showed that if the Byzantine hash rate or the Byzantine fraction of nodes is only alpha, then you're guaranteed a chain quality of at least 1 minus 2 alpha divided by 1 minus alpha. Now, back in lecture number 8, when we proved this guarantee, on the one hand, we were pretty happy because it strengthened liveness. It gave us better lower bounds, quantitative lower bounds on chain quality for all alpha less than 1/2. On the other hand, we were kind of annoyed that we didn't get the higher number 1 minus alpha, right? So if a 1 minus alpha fraction of the nodes or the hash rate is honest, right, naively you might hope that you'd have proportional representation of the blocks on the longest chain. And that's not what our proof showed. Our proof showed only a weaker lower bound on chain quality, a number smaller than 1 minus alpha, namely quantity 1 minus 2 alpha over 1 minus alpha. So that kind of bothered us at the time, but we did, we mentioned back then that in fact you cannot prove any better lower bound on chain quality than 1 minus 2 alpha over 1 minus alpha. The problem was not with our proof. The problem, or at least this is what we promised back in lecture number 8, the problem is actually there is a strategy for a Byzantine node that pushes the chain quality down to this lower number, 1 minus 2 alpha over 1 minus alpha. And this, here on this slide, this is the strategy that pushes the chain quality down to that lower number, down to 1 minus 2 alpha over 1 minus alpha. So in this lecture, right, we came to this strategy not really thinking about a Byzantine node like we were in lecture 8, rather just a sort of profit maximizing node that wanted to boost its share of the block rewards as much as possible by maximizing the fraction of its blocks that get on the longest chain. But if you think about it, that's the same goal as trying to minimize the fraction, minimize the chain quality, minimize the fraction of honestly produced blocks in the chain. And definitely this strategy is one thing a Byzantine node can do if it wants. So we can now reinterpret this strategy as something a Byzantine node could do to push the chain quality down to this lower number, 1 minus 2 alpha over 1 minus alpha. So in that sense, our chain quality guarantee for longest chain consensus back in lecture number 8 is tight. The number that we proved for all alpha cannot be improved further for that protocol. So it is actually an apples-to-apples comparison, our chain quality guarantee from lecture 8 and this analysis on this slide. In both cases, we are working in the sort of super-synchronous or instant communication model. In both cases, we were allowing arbitrary tie-breaking by honest nodes among competing longest chains. Right back in lecture 8, talking about chain quality, that's basically a liveness guarantee. We certainly didn't want guarantees that were sort of an artifact of some very delicate tie-breaking rule. We really wanted guarantees on chain quality that held for any possible way of breaking ties, which means that here, when we're proving that no better result is possible, we are free to assume arbitrary tie breaking, which of course is what we did in the analysis of the strategy to get the matching lower bound of 1 minus 2 alpha over 1 minus alpha. All right, so that's it for that digression, but I thought that was just sort of a really neat connection between basically our liveness analysis of longest chain consensus back in lecture number 8, and here basically the game theory of Nakamoto consensus with block rewards. It turns out those two things fit together quite neatly. So looking ahead to the rest of lecture number 10, there's going to be 2 more videos. The next video, the 5th video, that's going to be easily the sort of most difficult one, so you should regard it as optional. I mean, look, these are just free videos on YouTube, so in some sense, they're all optional. But if you're not excited about seeing some sort of interesting mathematical analysis, I would definitely skip the next video. Conversely, if you do like sort of interesting mathematical analysis, you definitely should check out the next video. That's really kind of the heart, and for someone like me, the really interesting part of selfish mining and the paper by Eyal and Serer. So whether or not you watch the next video, the 5th video, I definitely encourage you to watch the 6th and final video of lecture number 10. That's going to be a reasonably brief discussion of these selfish mining results. How should you interpret them? Do they matter in practice? All that good discussion is going to be in that 6th video. So whichever one you go to next, I'll see you there.